Hi, I'm Paragon. This is my programmable character output machine. So I'm going to start with a demonstration, and the first program is going to put an A in the left column, put a B in the right column, flood the screen with Bs, and then clear the screen. And let's watch it in action. It'll start repeating afterwards. Put an A in the left column, put a B in the right column, flood the screen with Bs, flood the screen clear, and repeat. A in the left. This is the current instruction. It flashes like down and left and right. That was because of I guess you would call them race conditions. Actually, only the one it becomes solid at is the instruction that gets used. I had to buffer the instructions, so I'll show how that works after I demonstrate my second program, which is going to set the value to C, flood the screen, and then I'm going to set it to a symbol, and then I'm going to print into the right column, and then I will print into the left column. Shoot, I did that backwards. Left column, right column. I know it's backwards, but 1 is left and 2 is right, so even though okay. So first we're going to set the character to C, flood the screen with C's, set to a symbol, print a symbol to the right, print a symbol to the left, and clear the screen. Excellent. So now a little bit of explanation of how it works. So right here is the output display. This is just a bunch of bulbs. The bulbs are connected directly to the output buffer. This would be this would be similar to a screen buffer. It's not actually necessary for two separate ones, but the bulbs are more compact than the latches, so that's why I did it that way. Over here is where I store the symbol. You can edit the symbol through the keypads here to make it whatever you want. And up here is where I store the characters. So there's the A, the B, and the C. I can continue with D, E, F. There's 5 bits of op data, so I could do a full 2 to the 5th is 2, 4, 8, 16, 32. Sorry, 32 characters. So I could do up to 32 characters, -1 for the symbol, and -1 for the empty character. So 30 symbols. Okay. So that was where we store the information. Over here, this is the instruction stack. We have instruction address 0. Every instruction has an opcode and op data. So opcode 0 is the null operation. Opcode 1 is to print a character. Opcode 2 is to set a character. And opcode 3 is flood the screen. There's only 2 bits of opcode, so I've only got 4 operations. I would have to add an additional bit to do anything else. On the right is the op data, so depending on which operation you're doing, it tells it what the data means. So for the null operation, the op data is irrelevant. For set character, you can put 1 is A, 2 is B, 3 is C. I would continue onwards. a 31 is the symbol, and 0 is an empty character. The print command takes either a 1 or a 2, where 1 is print to the left column and 2 is print to the right column. The flood screen does not take a value for op data because it doesn't need to. It's going to send it to all the characters, or send it out to all the columns. So there's the instruction stack. You program it by putting your opcode here and then the data. This is the instruction pointer. It points to the instruction that will be executed next. As you see, the next instruction to be executed will be at address 0. So if we look, address 0 is 10000011. That instruction is stored here, is buffered here, 10000011. And when the computer ticks, the buffered instruction gets pushed to the active instruction. Buffering it serves two purposes. First, it ensures that the entire instruction is calculated at once. Otherwise, you might have an operation working on data that it wasn't meant to. You might have the previous operation or the next operation working on the previous data until the current data gets updated. So that's why it's important to buffer and then push it all at once. So here's a little bit of view of the wiring. It's looks like a lot of wires, but it's mostly the same setup over and over and over again. So every single one of these instruction slots is exactly the same. It's easy enough to continue to add instructions. As you can see, I've only got alright. Well, as you can see, there's only 7 instructions, and I have a 4-bit instruction pointer, so it doesn't add up because I should be able to have 16 instructions. The reason that I only have 7 is because at address 6 I stopped building instruction stacks, and that was mainly because every time I save and quit or reload a character, everything gets a lot of my connections get lost. So it's been real frustrating trying to get this thing to actually work, because I can't die, I can't save and quit, and I can't leave the computer long enough for me to starve to death. So that's a real pain in the butt. Over here is this is actually a section for 2 operations. This gets turned on when it's the print character operation, and this is turned on when it's the flood character operation. So when this is on, okay, and then this triggers a pulse when the instruction is, when the op data is 1, and this triggers a pulse when the op data is 2. But in order to do so, the operation also has to be either one of these two. So you can see it has to be this operation, and the data has to line up. Or this one actually just has to be this operation, and it forces the pulse to both columns. If the opcode is set character, then this AND will be on. If the op data is all characters, or if is 31, then this AND will be on. So if this is on, and this is on, and this is not on, it triggers a pulse to toggle it. If this is on, and this is on, but this is not on, it triggers a pulse to toggle it again to turn it off. That way we don't have characters overwriting each other. No matter what, it has to be this instruction for any toggling to occur. So for configurable font, we could set up 5x7 panels and connect them directly to ands, and when this is on, this allows this information to pass through to either here, these are a bunch of latches, so either the data here, or actually it passes the information to both, and the pulse from the print character is the enable on these 70 latches, which means that if I'm enabling on the left, it'll set the data there. For this one, instead of being a configurable symbol or glyph, we have preset glyphs. So this is the preset glyph for C. As you can see, it only connects to the pixels that create the C. This is the B, so it is preset to connect to only the pixels that make up the B, and so on. So this works as in if it's the correct operation and the symbol is not on, and this, so with the symbol, the toggle latch connects to the data. So every pixel has data, and the enable is what is configurable. So even though the data is going through all of the pixels, the enable is only going to the ones that you define through the punch code. On the other hand, this one on the other hand, the latch, the toggle goes to, okay, I'm sorry, I said it backwards. On the glyph, on the configurable glyph, the latch, the toggle, is the enable, and the punch code, or the hand cards, go to the data, so that when this is enabled, so when it enables all of the pixels and only the ones you selected have data passing through them. On the other hand, the pre-configured glyphs, the data is sent to all of them, and only the pre-configured selection gets enabled. That way we can have the same data can be enabled in different configurations to yield different glyphs. There is a third method that we could use to build characters that I haven't implemented because, again, the fact that saving and quitting just destroys connections. And what we could have done is we could have added a new operation, and that operation could have been given 5 bits of data. Actually, we would need 2 operations. One operation would be to select which row that we are working on, and the other operation would have been to set which latches on that row. So we could have built a character through code line by line, and then once all 8 rows had been set, we would use the set character. So it would be a fully configurable dynamic character, but I didn't build that because the connections issue. And so here's all the connections again. Actually not all of them, because there's a bug, it seems, and actually it's not too bad of a bug, but like it actually helps out sometimes. But when you have too many connections on a screen at a time, sometimes, or if they're too far of a distance, they'll just disappear. See? So this is most of the connections, not all of them. You'll also notice that I'm zoomed in as far as I can, and that is because this particular machine causes quite a bit of lag. And so that's the machine. Thank you. Bye.